With sustainable design, construction, and operation in mind, we're designing a school building without compromising on energy conservation. The proposed school site is located in Bristol, with coordinates 51.5 degrees north and 2.6 degrees west. A brief site visit gave us an insight that the site is a relatively flat surface with no significant obstruction or overshadowing, little vegetation, and no mature trees within the boundary area. We're designing the school for a projected student population of approximately 1,700 students between 3 to 18 years of age for primary and secondary school. Bristol's climate data shows the outdoor temperature can get as high as 25 degrees Celsius during the summer and as low as -2 degrees Celsius during the winter, getting a significant amount of rain even during the driest month. Bristol receives at least 9 hours of daylight during colder months and up to 16 hours of daylight during summer. To maximize daylight gain, we first allocate spaces in compact blocks aligning towards the south. We then explode the blocks and assign their position according to their function, creating access in the process. With further geometry adjustments, we integrated orientation and facade considerations with daylighting principles. Now, when the structure profile is fixed and developed, each of the building blocks is linked to each other with connecting hubs.
Dalam mendesain sekolah ini, kami bertujuan.
For this project, we are treating energy efficiency as our top priority. After we have examined the site and fixed the position of each building, we began to allocate the room requirements, providing facilities necessary in the school. We focused more on the design of the primary and the secondary school buildings, as we believe those two buildings are the ones to be used most of the time throughout the year. The first aspect we took an account for is daylighting. The geometry of the two school buildings are set facing southbound to maximize sunlight gain during the day. The shape of the buildings themselves adopted the step roofing style to distribute natural light evenly throughout many sections of the buildings. Due to the lack of obstructions, we are countering glaring issue by forming additional shading that is provided by the overall shape of the building itself, especially on the secondary school building. We experimented on different types of facades until we found the best type to adapt with direct sunlight. We choose to combine meandering and reverse steps facade styles to prevent excessive sunlight from entering the building. Some parts of each building are embedded underground. We utilize earth sheltering concept to make use of the elevated grounds on site. Rooms such as storage, computer labs, and art studios which require minimum windows can be placed within. Integrating the earth as a building envelope helps the underground exterior temperature to be reduced, while maintaining indoor comfort. For the ventilation, harvested rainwater is transported and deposited at the underground compartment of the building, creating a medium to store heat absorbed from the surrounding ground. Wind encourages thermal buoyancy within the building, and mechanical fan is instigated when wind speed is low. As the temperature within the subground compartment is stable regardless of the change of outside temperature, inward-induced air subsequently distributes the exerted heat or cool from the water medium throughout the building. And then, the exchange of air occurs at the air vent located at ceiling and floors of each room. The stacked effect pushes the CO2 condensed stale air upwards and releases it to the outside atmosphere through the chimney.
遵循被动式房屋以及低碳。
We intend to reduce energy consumption by using low carbon and environmental friendly design method. Making use of the significant rainfall in Bristol, we also made the step roofing as a roof garden. The green roof mainly consists of 3 layers. The bottom grain layer is made up of minderball and filter fleece, which is then covered by the brown soil and the plant layer. Green roof not only helps slow down water runoff, it also contributes in reducing sunlight reflection and glare back into the sufficiently glazed area of surrounding rooms, while cooling down the building. On a study in Toronto, Canada, the membrane on an ungreen roof reached 70 degrees Celsius in the afternoon, while the adjacent green room remained at 25 degrees Celsius. The renewable straw bale walls used in our prototype can be locally sourced and responsibly, where it is shown to project the least embodied carbon among common building materials. We will base the structure out of straw bale layers enclosed on a hemline, with a U value that is lower than passive house standard. Straw bale walls not only have high insulating properties, which contributes to lowering excessive heat gain and heat loss in buildings, but also perform well in fireproofing compared to traditional foam insulation. Photovoltaic panels will be installed on flat roofs across the school to generate power for daily use, while cutting down use of electricity from the grid. The theoretical solar energy potential of the UK shows that Bristol can in theory generate power over 1,000 kWh per square meter annually, which means that with every square meter PV panel installed, it can potentially provide energy equal for running 4 computers every school day throughout the year.
The school construction production exhibits much potential for sustainable development, with more locals actively taking part in not only creating environmental awareness, but exploring the possibilities of constructing affordable and practical buildings as an effort towards a more sustainable future.